All right, Trig homework day 1 starts off with evaluating operations with absolute values. Keep in mind that an absolute value is the distance from 0 on the number line, so that the absolute value of 3 is saying how many places is 3 from 0 on the number line? Well, it's 3 places. And if I say what's the absolute value of -3, it's the same kind of thing. How many places is -3 from 0 on the number line? It's 3 places. Because absolute value is talking about a distance, our values are always going to become positive or 0 if it happens to be 0. So when we evaluate operations with absolute value, we want to evaluate so there's only one number inside the absolute value. It's not like parentheses that you can get rid of. You have to get it down to one number first and then evaluate the expression that's in the absolute value. So in this case, I would start here with the absolute value of 4 minus 15. I'm just doing the 4 minus 15. Inside the absolute value, 4 minus 15 is -11. So I have the absolute value of -11 minus the absolute value of -11. Again, you can't do minus a negative. You actually have to do the absolute value part. So the next step I'm going to do is evaluate my absolute values. The absolute value of -11 is 11. The absolute value of that -11 is also 11. And so my problem becomes 11 minus 11. And 11 minus 11 is 0. And so my answer for the first one there is 0. So if I'm doing the second one here, the absolute value of 4 minus 7 minus the absolute value of 10, again, I would start here and do inside the absolute value first. 4 minus 7 is -3. Then I would evaluate my absolute values. The absolute value of -3 is 3. The absolute value of 10 is 10. My problem now is what is 3 minus 10? 3 minus 10 is -7. And I got to move the board here for the third one. Evaluate the following. Now this one you'll notice has the extra absolute value on the outside, so we know our final answer is going to end up being positive. But if I go through my steps, inside my absolute value here, 1 minus 14 would be -13. Inside my absolute value there, 7 minus 3 is 4. So now I have the absolute value of -13 minus the absolute value of 4. Doing these absolute values on the inside. The absolute value of -13 is 13. The absolute value of 4 is 4. So now I have the absolute value of 13 minus 4. 13 minus 4 is going to be 9. And so the question is, what is the absolute value of 9? Well, my answer is going to be 9. Power rules with positive exponents, multivariate quotients. So using the power rule, where if I raise to a power, I multiply my exponents. I have multivariate, so many variables, and quotients, so I have a division problem in there. And so if I do my power rule, basically I have to raise everything to the third power. So I'm taking w squared to the third power, -2 to the third power, and u to the fourth to the third power. So we said with our power rule, w squared to the third power means I'm taking w squared times w squared times w squared. I add my exponents there and I get w to the 6th power. My power rule says if I'm raising to a power, I can just go ahead and multiply those exponents. So I'm going to have w to the 6th power up on top. Now with our number, we have to do it the normal way. -2 times -2 times -2. 1, 2, 3 negatives is negative. 2 times 2 is 4, and 4 times 2 is 8. So I get -8. And then I'm going to have u to the Again, I have to multiply those exponents, so 4 times 3 would be 12. Now, if I have a positive over a negative, that makes my whole fraction negative, so I have negative w to the 6th over 8u to the 12th. If you put it in with the negative on the bottom, the ALEKS program will say it's correct. However, the negative really should be out in front of your fraction, not on the top or the bottom of your fraction. So here again, if I'm using my power rule, again I'm cubing. I'm going to take the negative 3 to the 3rd power, the v to the 3rd power, and then the w cubed to the 3rd power. So negative 3 to the 3rd power would be negative 27. V raised to the 3rd power, v cubed. And then w cubed raised to the 3rd power, 3 times 3 is 9, so w to the 9th. Again, on that one, the better answer would be putting the negative in front. So negative 27v cubed over w to the 9th is how we would want to see that answer. Number 6 then, using my power rule, I'm going to square this one. So v to the 3rd squared, negative 3 squared, and then the u squared. So again, my power rule says I multiply my exponents, so I'm going to get v to the 6th. On the bottom, negative 3 squared. Negative 3 times another negative 3. Negative times a negative is a positive 9. And then the u squared is just u squared. So I get v to the 6th over 9u squared. Number 7, applying the power rule and the product rule of positive exponents. First thing we have to do is apply that power rule. Keep in mind if I have negative x to the 3rd, z to the 4th, that it's negative 1x to the 3rd, z to the 4th, and that I'm going to square that. So I'm going to take negative 1 and square it, x cubed and square it, z to the 4th and square it. So negative 1 squared, negative 1 times negative 1 is 1. I would multiply my exponents using my power rule, so x to the 6th and z to the 8th. I'm then going to multiply that times the 2x squared y to the 3rd z that I have in my other set of parentheses. So 1 times 2 is going to give me 2. When I multiply, I add my exponents, so x to the 3rd times, or x to the 6th times x to the 2nd would be x to the 8th. I don't have any y's in this one, but I do have a y here, so y to the 3rd. And then z to the 8th times z, z to the 9th. So my answer ends up being 2x to the 8th y cubed z to the 9th. Number 8, same kind of thing. I'm going to raise this to the 4th power. So I'm going to take the negative 1 to the 4th, the x cubed to the 4th, the y squared to the 4th, and the z squared to the 4th as my first step. So negative 1 to the 4th is 1. I get x to the 12th, y to the 8th, and z to the 8th when I multiply my exponents. I'm going to multiply that by the negative 2x to the 3rd y z to the 3rd. So negative 2 times 1 is negative 2. X to the 3rd times x to the 12th. I add my exponents. X to the 15th. Y times y to the 8th would be y to the 9th. And z to the 3rd times z to the 8th would be z to the 11th. Number 9 then. If I go ahead and do that one, my exponent is on the outside of the second one here, so I'm going to square everything. Negative 2 squared would be positive 4. Multiplying my exponents, I'd have x to the 6th, y to the 6th, and z squared. I'm going to multiply that by the negative 2, x squared, y squared, z to the 4th. So multiplying that out, I would have negative 8. X squared times x to the 6th. I add my exponents, so x to the 8th. Y is also going to be to the 8th. And z is going to be to the 6th. So 2 plus 6 is 8, 2 plus 6 is 8, and 4 plus 2 is 6. Number 10, 11, and 12, evaluating expressions with exponents of 0. An exponent of 0, basically what's happening is you've got something divided by itself. If I have x to the 4th divided by x to the 4th, my rule is to subtract my exponents. 4 minus 4 gives me x to the 0 power. But we know that anything divided by itself really cancels out. So by rule, anything to the 0 power means I'm taking something divided by itself, and I always get 1. So anything to the 0 power is always equal to 1. If I was going to do this on my calculator, I would do negative 2 fraction thirds to the 0 power. And if you put that in your calculator like that, you should see, yep, anything to the 0 power equals 1. Now if there's something in front of my expression, I have to do my exponent first. So 5 to the 0 power is 1, but there's a negative sign in front. So negative 5 to the 0 power equals negative 1. Here, 4 ninths to the 0 power is equal to 1. 3 times 1, going to give me 3. This one here looks very similar to that one there. 4 to the 0 power is 1. There's a negative sign in front, so I get negative 1. Number 12. If I do 2 to the 0 power, it's equal to 1. 1 times negative 2 is negative 2. And here I just have negative 1/5 to the 0 power. Notice the negatives on the inside, not on the outside. So if I take negative 1/5 to the 0 power, anything to the 0 power is equal to 1. My answer should be 1. The next ones are evaluating expressions with negative exponents with a positive fraction base. Negative exponent tells me that I have to do the reciprocal of the base. So anytime I see my exponent is negative, I'm going to flip my base and do the reciprocal. This is going to be equal to 7/5 to the positive 2 power. Now I can go ahead and do my power rule. 7 squared is 49, 5 squared is 25. So 49 over 25 would be my answer. Again, if you were doing that on your calculator, you would do 5 fraction sevenths to the negative 2 power. The calculator is going to give you the mixed number answer. Shift and the fraction button will change it into the improper fraction. Normally in algebra, we'll use improper fraction answers as opposed to mixed number answers. Of course, we want to get used to doing things without our calculator, but if you want to check with your calculator, go ahead. If I'm doing negative 1/2 to the negative 3 power then, the reciprocal of 1/2 would be 2 over 1. That'd make it 2 over 1 cubed. Well, 2 over 1 is the same thing as 2 cubed. 2 cubed is going to give me 8. If I do 4/5 to the negative 1 power, my reciprocal, 5/4 to the first power, and since it's to the first power, it's just going to stay 5/4. So negative exponents tell me to do the reciprocal of the base. 16, 17, 18 is doing the quotient rule with negative exponents. My quotient rule really says if I'm dividing, I can subtract my exponents. But what I like to do is get rid of the negative exponents by if it's negative, if it's on the top, move it to the bottom. If it's bottom, move it to the top. So I'm going to leave the 16 where it is because it doesn't even have an exponent. The 8 to the 7th, I'm going to move to the bottom because it was negative. I want to make it positive. The b to the negative 8, same thing. I'm going to move it to the bottom and make it b to the 8th. The c to the 6th, I'm going to leave on top because it is already positive. On the bottom here, I've got a 4. I have a b to the 4th, which is positive, so I'm going to leave that on the bottom. I have a c to the negative 2. I'm going to move it up to the top to make it c to the positive 2. So I've gotten rid of all my negative exponents by doing the reciprocal. Now I can combine. I'm going to have 16 c to the 8th on top, adding my exponents. I've got 4 a to the 7th and b to the 12th on the bottom. Now this one I can simplify just a little bit more because I can reduce the 4 and the 16. 4 goes into there once and into 16 4 times. So 4c to the 8th over a to the 7th and b to the 12th would be my answer in simplified form. Number 17 then, same kind of thing. Again, you could subtract your exponents on all of them. It does work. I just like to make my exponents positive first, just as a general rule. It makes things a little bit easier on here. And so on this one, I'm going to move the m to the 9th to the bottom, the n to the 5th to the bottom, the p to the 4th to the bottom. The m to the 7th is going to stay on the bottom. The n to the 6th is going to stay on the bottom, and the p to the 3rd is going to stay on the bottom. Well, what's on top then? We have to remember that the coefficients in front of these are 1s, so there is a 1 up on top of my fraction if everything else is moved down to the bottom. So combining my like terms, m to the 9th times m to the 7th would be m to the 16th. N to the 5th times n to the 6th is n to the 11th. And p to the 4th times p to the 3rd, p to the 7th. So my answer there, 1 over m to the 16th, n to the 11th, and p to the 7th. One last one of those here. If I'm simplifying this one again, I'm going to leave the 25. The b to the 7th is going to move to the bottom. The a to the 1st is going to move to the bottom. I wrote, don't really need the 1 there, but I'll write it there for fun. The 5 is going to stay. The a to the 5th is going to stay. But the b to the 4th is going to move up to the top. So I have 25b to the 4th up on top. On the bottom I have 5. I'm going to get a to the 6th and b to the 7th. Now this one I can reduce a little bit. I can reduce the 5 with the 25. 5 goes into there once and into there 5 times. And then I can reduce my b's. I've got 4 on top and 7 on the bottom, so if I take that 4 out of there, leaves me that extra 3 on the bottom. So my answer is that I have a 5 on top and a to the 6th, b to the 3rd down on the bottom. The next one's power and quotient rules with negative exponents, problem type 2. Again, if I have a negative on the outside of my parentheses, I'm going to go ahead and get rid of that negative first by doing the reciprocal of the base. So I'm going to make this 10x to the negative 6, y to the negative 4th, z to the negative 3rd, over 6x to the 6th, y squared, z to the negative 9. Now, this is going to be to the first power, so I really don't need to write it to the first power. If it was squared, I'd have to do the squaring, but since it's to the first, I don't have to do anything with that. Again, on this one, I've got some exponents that are negative, so I can go ahead and get rid of my negative exponents first. The 10 and the 6 are going to stay where they are. I'm going to move that x to the 6th down on the bottom. That x to the 6th is going to stay where it is. I'm going to move the y to the 4th to the bottom. The y squared is going to stay where it is. I'm going to move the z to the 3rd to the bottom. And I'm going to move the z to the 9th to the top. So, simplifying that mess, the 10 and the 6 I can reduce down. That would be 5/3. Here I'm going to have x to the 12th. Whoops, I'm trying to write my 12 before I write my x. X to the 12th. Here I'm going to have y to the 6th. And on my z's, I can cancel out 3 of them, so a z to the 6th on the top. So I'm going to have 5z to the 6th over 3x to the 12th y to the 6th. Still trying to write that 12. 3x to the 12th y to the 6th. Now keep in mind there are other orders and things you can do and solve it and still get the same answer as long as you're doing it mathematically correct. It really doesn't matter which order you do it in. I'm just doing it in the method I prefer just to keep everything straight so I remember what should I do first. So on this one, there is no negative on the outside. It's a positive 2 exponent. So I'm going to worry about the negatives on the inside. So on the inside, the a to the 3rd is going to move to the bottom. The b to the 5th is going to stay up on top. C to the 4th is going to stay on top. I didn't leave myself enough room. The b squared and the c to the 4th is going to move up onto the top. So simplifying what's inside my parentheses, I have b to the 7th, c to the 8th, over a to the 3rd, and I want to square that. So squaring that using my power rule, I multiply my exponents. I get b to the 14th, c to the 16th, and a to the over a to the 6th. If you look at that one, has a negative on the outside. So I'm going to get rid of the negative on the outside of the parenthesis first by doing the reciprocal. B a to the 3rd over 4a b to the 4th, and that makes my exponent positive. There are no negatives on the inside to get rid of. I can simplify on the inside first, or I can do my power rule first. It doesn't really matter, but I'm going to go ahead and simplify first. So one of my b's will cancel out, I'll get b to the 3rd. One of my a's will cancel out, I'll get a squared. So I have a squared over 4b cubed, all raised to the 3rd power. If I follow my power rule, I can go ahead and cube everything. So I'm going to have a to the 6th, 4 cubed, 4 times 4 times 4, 4 times 4 is 16, 16 times 4 is 64, and then b to the 9th. So I get a to the 6th over 64, b to the 9th. The next ones are working with scientific notation. Scientific notation is a way to write a long number in standard form in a shorter form by making a value that's between 1 and 10 or -1 and -10 times a power of 10. So it says a certain solution has a hydrogen ion concentration of 0.0000653 moles per liter. Write this number in scientific notation. So in scientific notation, I'm going to put my decimal behind the first non-zero digit. So I have 6.53. 6.53 is a value that's between 1 and 10. I'm going to multiply that by a power of 10. And so what I'm doing is thinking about, well, if I had my decimal here, to get it back to the original spot, I have to go 1, 2, 3, 4, 5 places backwards. Since I have to go back 5, I'm multiplying by 10 to the -5th power. So on your calculator, if you did 6.53 times 10 caret -5 and you hit equal, it should give you the number in standard form as long as it's not too long for your calculator screen, which should be 0.0000653. Part B of that, a black rhinoceros can weigh up to 6.4 times 10 to the 3rd pounds. Write this number in standard notation. So basically all I'm doing is multiplying by the 10 to the 3rd, which moves my decimal 3 places to the right. If I have 6.4 and I move it 1, 2, 3 places, that's 6,400 pounds. 23. It says an astronomer's infrared telescope is able to detect radiation with a wavelength of 5.32 times 10 to the negative fourth meters. Write this number in standard notation. So I have 5.32. I'm multiplying by 10 to the negative 4, which moves my decimal to the left 4 places. 1, 2, 3, 4. So I have 0.000532. But in best form, we always put that 0 in front of the decimal. It just looks prettier. And if you use your calculator, you'll see the calculator puts a 0 in front of the decimal. Part B of that, the diameter of Saturn is at the equator is approximately 121,000 kilometers. Write this number in scientific notation. So my decimal is going to go behind this first digit, 1.21. I can drop off all those extra zeros, which shortens my number up, times 10 to the, and if I moved it here to get it back to where it originally was, I'm going 1, 2, 3, 4, 5 places to the right. So it's going to have a positive 5 exponent. So 1.21 times 10 to the 5th would be my answer there. So number 24 again, the signal from a certain satellite takes approximately 0.0081 seconds to reach the Earth. Write this number in scientific notation. So my decimal is going to go behind the 8, 8.1 times 10 to the, if I put it here to get it back to where it originally was, I'm going to go 1, 2, 3 places to the left or 3 places backwards. So 8.1 times 10 to the negative 3. And the total surface area of North America is approximately 9.54 times 10 to the 6 square miles. Put the number in standard notation, 9.54. I want to move my decimal 6 places to the right. 1, 2, 3, 4, 5, 6. So I'm going to have 9,540,000 if I move my decimal 6 places to the right. So 25, 26, and 27, multiplying a multivariate polynomial by a monomial. Monomial, we just have one term in front. Polynomial, we have many terms in the parentheses. Basically, we're just doing our distributive property. So we're going to multiply this times this, this times this, this times this, and get our 3 answers. We're multiplying the coefficients, adding the exponents on our variable. So negative 8 times 3 would be negative 24. B times b to the 5th would be b to the 6th, and c to the 4th, there's no extra c's, I still have to have that c to the 4th. So my first term, negative 24, b to the 6th, c to the 4th. My second term, negative 8 times negative 2 is positive 16. We do need to put that plus sign since it's not the leading term. I'm going to get b to the 4th, and then c to the 4th times c squared, c to the 6th. Then my last term, negative 8 times negative 9 is a positive 72. I have a b, no extra b's there, but I still need the b in my answer. C to the 4th times c squared, c to the 6th power. So negative 24, b to the 6th, c to the 4th, plus 16, b to the 4th, c to the 6th, plus 72b c to the 6th, going to be my answer. Number 26, using my distributive property, again, my monomial happens to be behind it, but that's okay. We're still multiplying that by each of our terms in the parentheses. So 9 times negative 7 would be negative 63. A to the 5th times a is a to the 6th. B to the 6th times b to the 4th, b to the 10th. Negative 8 times negative 7 is a positive 56. I have a to the 3rd times a, which is a to the 4th. That doesn't have any b's, but that has b to the 4th, so I still have to have the b to the 4th on my answer. And so I get negative 63 a to the 6th b to the 10th plus 56 a to the 4th b to the 4th for my answer. And 27, same kind of thing, multiplying that out. So 5 times 4 is 20. I have just a w, x to the 7th. 5 times negative 2 would be negative 10. I'm going to get w to the 4th, and I still have the x squared. And then 5 times 9 is positive 45, and I have the wx squared for my first term. So my answer, 20wx to the 7th minus 10w to the 4th x squared plus 45wx squared. And the last three are multiplying binomials in two variables. That thing that we always called foiling all through algebra class. And so we're multiplying the first, the outside pair, the inside pair, and then the last, and then combining our like terms. So the first pair, 5a times 5a, 25a to the 2nd power. The outside, 5a times 8b, positive 40. We like our variables in alphabetical order, so positive 40ab. And then the inside pair, negative b times 5a, would give me negative 5. And again, instead of putting negative 5ba, I'm going to put negative 5ab. So I recognize I have like terms. And then negative b times 8b, negative 8b squared. Combining my like terms in the middle, I'm going to have 25a squared plus 35ab minus 8b squared for my answer. So 25a squared plus 35ab minus 8b squared. Second one, foiling that one out. 4y times 8y, 32y squared. 4y times the negative 3z, negative 12yz. Negative 3z times 8y, negative 24yz. And then negative 3z times the negative 3z, positive 9z squared. Combining my like terms in the middle, I get 32y squared minus 36yz plus 9z squared for my answer. And number 30 here, foiling that one out, x times 5x is 5x squared. X times negative 8w is negative 8wx. And if you put negative 8xw, it's the same thing, just be consistent. 3w times 5x, 15wx. 3w times negative 8w, negative 24w squared. So combining my like terms in the middle, I have 5x squared. 15 minus 8 would give me positive 7wx minus 24w squared. And that's going to be my answer. Hopefully when you took your pretest you already knew how to multiply binomials, and they might not show up on your pie chart, but if they do, there's some examples.